Welcome to the structural dynamics, the free vibration analysis of structures. So the structural vibration is caused by the dynamic loads such as the wind, the earthquakes, the waves in the ocean, or the vehicles, moving vehicles called traffic, or trains, and rotating machinery. Apart from this, the operations like pile driving activity can cause vibration to the structures, and blast operation can also cause vibration to the structure. So what is the difference between this so far? I mean, difference between static and dynamic. So as far as the static analysis is concerned, the static in terms of the applied load, difference in terms of applied loads, that means the load is constant, whereas in dynamic, load is varying with the time. Okay. Now the magnitude of the force is also the constant. Here the magnitude of force, some point less, more, is varying. And also the direction, the force direction is downward static. Here force direction can be sometimes upward or downward. So this is the difference between the static and dynamic analysis in terms of the applied load. So now the difference can also be seen from with respect to the response obtained from the analysis. So in terms of response, so in the static analysis, what response we get? We get a displacement, we get a velocity and acceleration. But when in static analysis, we get only displacement, we don't get velocity and we don't get an acceleration. Whereas in the dynamic analysis, we get displacements with the time, right? So every displacement with the time, velocity with respect to time, and acceleration with respect to time. So, right, and apart from that, the mass under the acceleration produces inertia force. This is additional thing which is in the dynamic, which is not in the static. So you are going to get additional force called inertia force. You are going to get additional force called inertia force in the dynamic analysis, which you neglected in the static analysis. So this is as far as the analysis of a dynamic and a static in terms of their response. So as I mentioned, that inertia force is additional in the dynamic analysis. Now, so and in the dynamic analysis, there is an important factor called degrees of freedom. That is the independent number of displacement components required to represent the system for the significant inertia forces in the structure. So according to the degrees of freedom, that inertia force is the significance inertia force is contributing. We can divide the structure into single degree freedom system, multi-degree freedom system, and a continuous system. The single degree freedom system, like I can think of a single story building or a water tank. Multi-degree freedom system can be a multi-story building, 3-story or 4-story. Each of the story can be taken as 1 degree of freedom. But this is like a lumped mass at the story level. But most of the times we may not have lumped mass at a story level to represent the degree of freedom. Such a system is called continuous system, like the continuous beam, cantilever beam, or simply supported beam, or a tower, So for those structures, so there is no lumped mass at one point. It is continuous throughout the structure. So we need to model that with help of a continuous system. So what is the single degree freedom system? The equation mathematically, that single degree freedom system equation of motion can be written as the mx double dot cx dot kx equal to f of t. So this mx double dot is inertia force, the cx dot is a damping force, kx is a stiffness force or spring force, and f of t is the external force acting on the system. That means all these three are internal forces and this is the external forces, and that has to be balanced as per D'Alembert's principle. So the m is a mass element which is representing the inertia characteristics of the structure. The spring, which is k, represents the elastic restoring force and potential energy capacity of the structure, and c is a dash part, represents the frictional characteristics and energy loss of the structure, right? Then f of t is the external force, represents the external force on the structure. Okay, so now if you look at carefully, the all internal forces, as I mentioned, the inertia force into internal forces, f of this stiffness force fs is k into x, and ft is the damping force, which is cx dot, and this has to be balanced by the external force called f of t. So when you try to draw the free body diagram of the structure, so what we see, inertia force and spring force and damping force, and has to be resisted by the external force, and that is this, the fi plus fd plus fs is equal to f of t, which is your D'Alembert's principle. Okay, so when you try to plot a curve between fs and the x, will get a stiffness k. When you plot between fd, damping force versus velocity, will get a c, damping coefficient. When you say inertia force with respect to the acceleration, you get mass is a coefficient actually. So this is all assumed to be linear. Sometimes system may not be linear. Okay, so now, so depending upon the kind of the parameters involved in the system and the external force present and non-present, we categorize the vibration into two. Depending upon the external force present and non-present, the external load is not there, which is f of t 0, we call it as free vibration. When external force is there, then we call it as force vibration. So within this, when external force is not present, and if you are not considering the damping in the system, we call it as undamped vibration. If you consider the damping, we call damped vibration. Similarly, in the force vibration also, damping is not considered undamped vibration, damping is considered damped vibration. So accordingly, I wrote here the equation of motions. Mx double dot plus kx equal 0 is undamped free vibrations, and this is damped free vibrations. Damping means this term is there. Okay, so here external force is there, we call it as force vibration. So that external force also in terms of time. So now the equation of motion, what we saw, mx double dot plus kx dot equal to 0, those equation of motions can be derived using simple methods called simple harmonic method motion, wherein acceleration is proportional to my displacement but in the opposite direction. That's all. Just using this, I can derive the equation of motion. Second one is a Newton laws of motion, which is again inertia force is again proportional to your spring force, but is in opposite direction. Then using energy methods, that means total energy is constant in the system. Energy law of conservation of energy, right? So using that potential energy and kinetic energy, so is constant. So taking the derivative of that, and we'll get the again mx double dot plus kx equal to 0. And we can also use a Rayleigh's method, wherein you assume a certain solution and differentiate that and use the Rayleigh method to get the equation of motion again. Or you can use the D'Alembert's principle directly, which is the inertia force, damping force, and spring force are internal forces, and the P of T is external forces, and equating them is nothing but the equation of motion. So these are 5 ways we can derive the equation of motion. So now this is the as far as deriving the equation of motion is concerned. How about the response to the free vibration? So now I'm going to talk about the response. Talking about the response to undamped and damped. 2 things we discuss. So undamped and damped. So first let us discuss about the undamped vibrations. So the undamped means damping term is not there. So there is no C term here. So very important while deriving this. So what must cause the excitation to the structure? So that we call it as the initial conditions. The initial disturbance to the system is required. So how are we going to cause initial disturbance? To find out the response. So the initial condition called initial displacement and initial velocity. Sometimes you may cause only initial velocity, sometimes you may cause only initial displacement. Okay. So the equation of motion will be mx double dot plus k is equal to 0. Now, since we know this motion is like a harmonic, right? So which is kind of a sine or cos. So the assumed solution will be x of t equal to a sine omega nt plus b sine omega nt. A cos omega nt plus b sine omega nt. So a and b are the constant which can be obtained from initial conditions. So we have 2 unknowns and 2 conditions. So I can obtain a and b. So taking in the differentiation, that get a velocity, and you have the initial velocity value, which is your maybe u naught, initial displacement maybe x naught. So substituting that, so at time t is equal to 0, initial displacement is x naught, initial velocity is u naught. So you get a and b, a equal to x naught, b equal to u naught by omega n. By substituting back to the assumed solution, so I get this, and this having 2 terms, something and cos and something in sine, I can put in the single form, which is your rho into sine of omega nt plus alpha. That is easy to understand in a single function. Okay. So this we can understand using, so that rho is like amplitude of the vibration, which is the maximum amplitude, which is this. This is the distance is rho, maximum amplitude, which is x naught is the initial displacement, u naught initial velocity, which is known to us. So initial displacement is your this is your x naught here, this is a x naught, and when you draw a tangent at t equal to 0, so I get slope, that is slope nothing but initial velocity, right? So this is your maximum amplitude is your rho, and from any peak to peak is your time period capital T, which is 2 pi by omega n. Omega n is the natural frequency, t is the time period of the structure, and alpha is a phase lag, which is nothing but when you extend this curve to the x-axis negative side, which is alpha by omega n, that is a phase lag. So it can be obtained from this tan inverse of x naught by u naught by omega n. So this is as far as undamped system is concerned. Now the damped system, how does the system responds to the damping? So this is again a response. To know at what time the system is where. So this is a mathematical modeling of this damped. So this is an additional term into the system, and anyway external force is not there. So this is a free body diagram, right? So mx double dot plus cx dot plus kx equal to 0. Now this thing is, with this equation of motion, the assumed solution will be is this. We know the system is having response different because of damping. System slowly comes to rest. So initially with high amplitude comes to 0, right? So that is what we need to represent properly. So that is your exponential terms, exponentially decay. So a into e power st. So somehow these two are, a and s are the constant which can be derived from again initial conditions, which is initial displacement and initial velocity. So you take differentiation of this, another differentiation of this, and substitute all into the equation of motion, and you'll get this equation here: a into e power st ms square plus cs plus k equal to 0. So then, and that ms square plus cs plus k equal to 0. So this is the term which gives you a quadratic equation, and it has two roots of s, which is s1 and s2, and depends upon the negative roots, imaginary roots. So we get the three different responses called over damping, critical damping, and then under damping. Under damping is not undamping, under damping. So these things can be learned. This over damping, see, look at here. So there is no vibration at all in the over damping, and critical damping also something like this one. Maybe something like this. Taking longer time to come to rest, but it is not going to cause any vibration. So this is your critical damping. Critical damping. But these are not a civil structures. These are mechanical system wherein damping will be more than 100%. So civil structures have very less damping, which is called under damping, which is around 20%, maximum of 20%. Okay. So the response will be something like this. So slowly it is coming down. So if you try to draw take the points of pick the points of peaks and under the plot, it is exponential decay. It is exponential decay plots. So this exponential decay is called logarithmic decay. So this is the response to the damped system. And if you try to see the difference between the undamped and damped very clearly, this is what you need to note very carefully. Initial velocity is the same. Displacement, you may provide the same displacement d0 and d0. The exponential decay is what you can observe here. Here what you observe is constant amplitude, which is not desired. This is constant amplitude. We don't want it. So in the case of damped system, the amplitudes are getting reduced. And one more thing you can see, the time period of the system is the same. That means as far as when damping value is up to 10%, for a concrete it is 5%, for concrete structures, for a steel structures it is 2%. So it's very less. So if you take the 5% damping, so that means basically the time period for the either damped or undamped is the same. Time period remains same. Okay, so that means your frequency remains same. So that is why the damped frequency is natural frequency times 1 minus under root of 1 minus xi square. Xi is damping ratio. So this factor is close to 1. That is why omega d is very close to omega n. So natural frequency is close to your damped frequency. So this is what we can observe from the undamped and damped responses. Thank you so much.